Okay, so welcome to this next video in which we are discussing the different types of lipids. Okay, so we're in the process of discussing the phosphoglycerolipids. Okay, specifically we now want to look at the structure of phosphatidylglycerol. Okay, now phosphatidylglycerol will consist of a phosphatidic acid molecule linked to a glycerol molecule. Okay, so here is our glycerol molecule here, and we were just in the process of discussing the optical isomerism of the phosphatidylglycerol molecule, i.e. whether the alcohol group will come out of the page and the hydrogen go into the page, or whether the hydrogen will come out of the page or the alcohol group will go into the page. And basically it's that the alcohol group will come out of the page towards you and the hydrogen will go into the page away from you. Okay, like so. So here is the hydrogen going into the page away from you. Right, so that's the structure of phosphatidylglycerol then. Okay, now let's talk about the next phosphoglycerolipid. Okay, and the next phosphoglycerolipid I wish to talk about is another quite famous one, which is usually just abbreviated to PIP2. Okay, and this stands for Phosphatidylinositol 4,5-bisphosphate. Okay, so the P is for phosphatidyl, the I is for inositol, and then the P2 is for 4,5-bisphosphate. Okay, so it denotes the two phosphate groups that you have coming off the inositol ring. Okay, right. So basically, what you're going to now do is attach onto your phosphatidic acid molecule an inositol ring, which will have two phosphate groups coming off it, which will come off the fourth and the fifth carbon of that inositol ring. Okay, so let me now show you the structure of the inositol ring that we're going to put on. So basically, the chemist's name for inositol is to call it cyclohexane 1,2,3,4,5-hexol. Okay, so cyclohexane 1,2,3,4,5,6-hexol is the proper chemist's name for inositol. And again, although this is a mouthful, it's a better name for inositol because it tells us exactly what we're dealing with here. It tells us that we are dealing with a six-membered carbon ring, like so, where you have alcohol groups coming off every single one of the carbons in that six-membered ring. So here's our six-membered ring where we have single bonds between all the carbons in the ring, and we're going to have alcohol groups coming off every single one of the six carbons in that cyclohexane ring. Okay, right. Now, basically, cyclohexane 1,2,3,4,5,6-hexol, or inositol, is going to have a great many optical isomers, because if you imagine the six carbons here sitting within a plane, then each of these carbons is going to have a hydrogen atom coming off it and also an alcohol group coming off it. Now, either all of the alcohol groups can go into the page away from us and all the hydrogens can come out of the page towards us, or you can have mixtures. Basically, you could have two alcohol groups coming out of the page towards us, whilst the other four go into the page away from us. So basically, there are a great many optical isomers of inositol. There are actually 9 different optical isomers of inositol. The optical isomer of inositol, which is important within cells, is called Myo-Inositol. So let me tell you what Myo-Inositol is going to have as far as the optical isomerism of the alcohol and hydrogen groups coming off these carbons is concerned. So basically, off this first carbon here, we will draw an alcohol group coming out of the page towards us, which means that the hydrogen coming off this first carbon will be going into the page away from us. Then of this second carbon here, we'll also have the alcohol group coming out of the page towards us and the hydrogen going into the page away from us. Of this third carbon, again, we'll have the alcohol group coming out of the page towards us and the hydrogen going into the page away from us. So all of these alcohol groups are on the same side of the six-membered carbon ring, basically, or the plane in which the six-membered carbon ring is in. Okay, then off the fourth carbon here, the alcohol group coming off that will be going into the page away from us, like so. Okay, then off the fifth carbon here, the alcohol group will be coming out of the page towards us, and the hydrogen will going into the page away from us. And then finally, off this sixth carbon, you will then have the alcohol group going into the page away from us. This is the structure of Myo-Inositol. Okay, so you have 4 of the alcohol groups on one side and 2 on the other, and the 2 on the other have a single alcohol group that's coming out towards us in between them, basically. Okay, so that's Myo-Inositol. Now basically there is a set naming system for the carbons within Myo-Inositol. This one here is called carbon 1. This one here is called carbon 2. This one here is called carbon 3. This one here is called carbon 4. This one carbon 5. And this one carbon 6. Okay, so that's the set in stone naming system of the carbons in Myo-Inositol. And this is the one we are now going to attach onto a phosphatidic acid molecule. So basically, we are going to attach this alcohol group here to the phosphate group of the phosphatidic acid molecule via a phosphoester link. So let me show this on the other side. So basically, let's just quickly draw out the phosphatidic acid molecule again. So remember, the phosphatidic acid molecule consists of this 3-carbon backbone, which is from the glycerol, and then off all of the alcohol groups, well, off 2 of the alcohol groups rather, you have these carboxylic acid groups which have been esterified on, like so. So here's the first carboxylic acid group, and here is the second one here. And then we'll saturate these carbons here with hydrogens, and then off the 3rd carbon of the glycerol molecule, you then have a phosphate group linked to this oxygen via a phosphoester link. Okay, like so. So here's the phosphorus atom with a double bond to an oxygen, a single bond to an oxygen which has acquired an electron via ionic means, and then we would have an alcohol group here, but this alcohol group is going to be now involved in a phosphoester link onto our Myo-Inositol ring. Now I'm not going to bother drawing the optical isomerism anymore, but remember this is the first carbon of our Myo-Inositol ring, so if we just remind ourselves of the optical isomerism, the alcohol group is coming out of the page towards us. Okay, so that would be what is known as phosphatidyl inositol, but we want phosphatidyl inositol 4,5-bisphosphate. So basically, we are going to have phosphate groups coming off the alcohol group of this 4th carbon, and remember the alcohol group of this 4th carbon is going into the page away from us. Okay, so again, the phosphate group has just been attached via a phosphoester link. We're going to have nothing coming off the alcohol groups of the 2nd and 3rd carbon here. Off the 5th carbon, we're not going to have anything coming... Oh, sorry, we are going to have something coming off the 5th carbon. We want phosphatidyl inositol 4,5-bisphosphate. So we are, in fact, going to have a phosphate group coming off that 5th carbon's alcohol group here, like so. And then it's the 6th carbon which we're going to have nothing coming off. Okay, and I should really show the hydrogens because I have drawn a molecular formula here rather than a skeletal formula. So we'll also have hydrogens coming off all of these carbons. Okay, right. So this now is the structure of phosphatidyl inositol 4,5-bisphosphate, or PIP2. So these are the major phosphoglycerolipids, basically. We've seen phosphatidyl choline, phosphatidyl ethanolamine, we've seen phosphatidyl glycerol, and phosphatidyl inositol 4,5-bisphosphate. And of course, we've also seen phosphatidic acid itself. Okay? Now, all of these phosphoglycerolipids are major components of the lipid bilayer, basically. Okay, and they are all considered phospholipids. So, what is the difference between a phosphoglycerolipid and a phospholipid? Basically, a phospholipid just means a lipid molecule which has a phosphate group. So basically the characteristics that you have to have in order to be characterized as a phospholipid is you need at least one, okay, so greater than one long chain carboxylic acid or one fatty acid. So you need within your structure at least one fatty acid molecule, basically. So we can see, for instance, looking here, we've got 2 fatty acid molecules here in all of these phosphoglycerolipids. So they certainly satisfy that condition. And then you also need at least one phosphate group. Okay, and that's all you really need to be considered a phospholipid, a fatty acid molecule with a phosphate group at some point in your structure. So these need to be within your structure. The characteristic that you need to be a phosphoglycerolipid is that you need to have this phosphatidate molecule within your structure. Okay, so basically you need to be based on glycerol. Okay. So these are phosphoglycerolipids, and these are all based on phosphatidic acid molecules. Okay, right. So what we're now going to move on to is the next category of lipid molecules, which are sphingolipid molecules. Okay, and we're going to see examples of phospholipids within the category of sphingolipids. Okay, so this is why you should not think of phosphoglycerolipids as being the only examples of phospholipids. Yes, when people generally talk about phospholipids, they generally draw you a little cartoon that resembles a phosphoglycerolipid, but phospholipid is actually a broader term than that, and certain sphingolipids will also meet these characteristics that you need to be considered a phospholipid, okay, and they will also be present within the lipid bilayer. So the lipid bilayer isn't just one type of lipid molecule, it's many types of lipid molecules. You'll have all of these phosphoglycerolipids that we've just discussed within the lipid bilayer. You'll have some triacylglycerol molecules within the lipid bilayer, although they're not that common within the lipid bilayer. And you're certainly going to have sphingolipids within the lipid bilayer. Okay, so we now need to discuss what is a sphingolipid. So basically, in order to discuss what a sphingolipid is, we firstly need to discuss what the structure of sphingosine is. Okay, then we need to discuss what a ceramide is, and then we can finally go on to what a sphingolipid is. Okay, so sphingosine. The proper chemist's name for sphingosine is to call it 2-amino 4-octadecene 1,3-diol. Okay, so 2-amino 4-octadecene 1,3-diol. Okay, and you shouldn't be scared of this name. This is actually extremely simple. This tells us that we're dealing with an 18-carbon molecule which has a single double bond, okay? This tells us that that double bond is between the 4th and the 5th carbon, okay? This tells us we've got an amino group coming off the 2nd carbon, and this tells us we've got alcohol groups coming off both the 1st and the 3rd carbon. Okay, so let's go in and draw this structure. So actually the only interesting carbons in this entire structure are the first 5. They've got the interesting structure. The rest of the carbons are all just saturated. Okay, so after that the other 13 that are left are just really boring. So we're going to have 12 methylene groups. Okay, which I'll draw just by drawing one methylene group, then put brackets around it and subscript it 12. You should be used to that trick now. And then right on the end we'll just have a methyl group. Okay, right. Now, we then have a double bond between the 4th and the 5th carbon here. That's the 4-ene bit here. So in fact, I think I might try and highlight the different portions of the structure that correspond to the different portions of the name. Okay, so the 4-ene refers to this double bond between the 4th and the 5th carbon, like so. Okay, right, let's now do the 1,3-diol. So we've got 1,3-diol, so we need an alcohol group coming off the 1st and the 3rd carbon. Okay, so we'll have this like so. So, here's one alcohol group, here's the second, and now we'll deal with 2-amino. So we need an amino group coming off the second carbon, we'll have that here. And now let's just saturate everything else up with hydrogen atoms. So I have 2 hydrogen atoms off there, 1 hydrogen atom off there, and 1 hydrogen atom off there. So that's the amino group here. So finally, let's just make sure that this makes sense now. Firstly, have we got an 18 carbon molecule? Well, 1, 2, 3, 4, 5. Then we've got these 12, that'll take us up to 17, and then 18, so that's ticked off. We've got our 18 carbons. We've got our double bond between the 4th and the 5th carbons. We've got alcohol groups coming off the 1st and the 3rd, and we've got amino groups coming off the 2nd. Okay, so this is 2-amino, 4-octadecene, 1,3-diol, or sphingosine. Okay, and we're going to see in the next video how we can use sphingosine as the backbone for creating ceramides, and then how we can use ceramides as the backbone for creating sphingolipids.